Today's lecture will be on rotation and rigid body physics. So in rotation and rigid body physics, instead of an object going in a straight line fashion from point A to point B, the object is now spinning around. So let's start by defining a rigid body. A rigid body means that this object does not deform or twist in any way when it moves. Every point on this wheel is maintained and rotating together. The distance between that point and the center of mass, or the middle of that wheel, is the same throughout the rotation. There's 3 different types of rotational motion, and the first one is translational motion, which means that the object as a whole moves along a trajectory but does not rotate, but the object stays in its same original form. The second type is rotational motion, where the object rotates around a fixed point. Every point on the object moves in a circle, and generally this point is either the center of mass, the end of an object, or just the middle of the object. And the third type of motion is combination motion, when an object rotates along a trajectory. So it moves in a projectile type fashion while also rotating around some point. An example of this is throwing up an expo marker into the air, and that's a good type of combination motion. And then in rotational motion, there are 3 key variables that are used. Theta, which represents the angular position, omega, which represents angular velocity, and alpha, which represents angular acceleration. Angular acceleration is how quickly or slowly the object is spinning. Angular velocity is how fast the object is spinning. And theta, the angular position, is measured in radians, and it can represent the distance. The 3 main equations that are used in rotation is S equals R theta, velocity equals R omega, and alpha equals R alpha. If a point of distance r from the axis of rotation, then this point moves along a circular arc length s, and its tangential velocity is v, and tangential acceleration is alpha. Everything here depends on the radius and is scaled by this value. Just like we had the big 3 kinematics equations for linear motion, we also have kinematics equations for angular motion. So these equations are very similar to those of linear motion, except we replaced x with theta, v with omega, and acceleration with alpha. Our next topic for this lesson is torque. And torque is the rotational acceleration like force does in linear motion. Torque is what causes things to move for rotational motion. The formula for torque is R cross F, which is RF sine theta, and torque depends not just on the force applied, but where you apply it, and that's where the radius comes into the equation. For example, if you push on the center of a door, then it's not going to move. However, if you use the same amount of force to push at the edge of the door, then it will swing open, and that is an example of torque in action. So rotational motion also has a version of Newton's second law, and that equation is T net equals I alpha, where I is the moment of inertia and alpha is angular acceleration. Moment of inertia has a different equation for different types of shapes. For example, a solid disk has the equation 1/2 mr squared. A rod where the point of axis is at the center has the equation of 1/12 ml squared. And along with this, there's also the parallel axis theorem for when the axis is not at the center of mass. And that equation is I equals I center of mass plus md squared. And then for energy and angular motion, there's 2 equations we can use to calculate this. For rotational kinetic energy, the equation is 1/2 IW squared And for angular momentum, the equation is L equals I omega. And both are conserved in the absence of external torque, just like linear motion, linear momentum, and energy. So the first step to finding the angular acceleration for this problem is using the moment of inertia formula for a solid disk. And when you plug in the values given to us into 1/2 mr squared, you get 0.25 kg meter per meter squared. And then we use the torque formula to find the amount of force applied, which is 5 newtons. And then we use the formula for angular acceleration, alpha equals r over I, which is 5 over 0.25, which gives us 20 radians per second squared as the angular acceleration. To find the angular velocity, we used one of the new kinematics equations, omega equals initial omega plus alpha t. We substituted the given values, 20 for the acceleration that we found earlier, and t3 for time, to get 60 radians per second, which is the angular velocity. Next, to find the rotational kinetic energy for this solid disk, we used the formula, which is 1/2 I omega squared, which is 1/2 times the moment of inertia, which was calculated earlier, times omega squared, which we just calculated. Substituting those two values, we get 450 joules, which is the rotational kinetic energy. Some real-life applications of rigid bodies and rotation are gears, wheels and braking systems, spinning balls in sports, Ferris wheels, roller coasters, and other amusement park rides, and tools and devices like power tools and blenders. All of these things take into account rigid body and rotations.